Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello friends, today I'll show CFD parametric study and optimization of a centrifugal pump. The impeller shaft is having diameter 25 mm and the impeller will be rotating with varying angular speeds. And in this parametric study, we'll consider different varying speeds, and with respect to different varying speeds, we'll find out pressure, temperature, velocity, etc. at the exit locations. For better understanding of this model, let us cut this model along some specific planes. Initially, we'll cut this one from this front plane. You can see this is the impeller. The shaft diameter is 25 mm. In this analysis, we have to find out shaft torque also, and by the same time we have to find out pressure, velocity, temperature at the exit location. This is the exit location and this is the inlet location. So for understanding the inlet location, we can cut it along some other planes. Let us cut it from right plane. You can see that this is the inlet location, and what will be passing from this inlet, and through this impeller it will be moving off along this path, right? You can see the impeller. Okay, so let us start this one. The leads have already been provided to create a closed geometry, and the flow simulation environment you have to create with the wizard itself. Let's start from wizard and keeping the name of the project as default project 3. Next, the unit system will consider as SI, and pressure will be considered in bar, and temperature will consider in degrees centigrade, and consider angular velocity as revolutions per minute. Next, it is an internal analysis, and definitely gravity will be involved, and the direction of gravity will be y. Along y direction it will be minus 9.81 meter per second square, and along z direction it will be 0. Definitely rotation will be involved in this case. Next, we'll consider water as the liquid. Next, default water thermal conditions and roughness we are considering. Thermodynamic parameters will consider temperature as 20 degrees centigrade. Let us finish this. You can see this is the computational domain. We can edit this part to ascertain that all the centrifugal pump should be inside this domain. So we can make this domain a little bit bigger. Let us edit this part. Computational domain, edit definition. We can extend these things a little bit bigger to ascertain that all the centrifugal pump should be inside this computational domain. It is done. Green check. Now we can hide this part, and we have to provide some boundary conditions. And for providing boundary conditions, it is always suggested to have a segmented view of this model. So now we can cut this model across some specific planes. Let us cut this one from front plane and drag it. Green check. Initially, you have to provide the rotating region. The impeller will be rotating with 1000 RPM, so we are providing that one. And one thing, to provide the rotating region, we have made one dummy space that is hidden at this moment, that to be shown for providing rotating region. Insert rotating region, and that will be rotating with an angular speed of minus 1000 RPM. And let us select that dummy space from the geometry. It is written as dummy impeller space. We have to show that dummy space. The dummy space is visible now. Now rotating region we can provide. Insert rotating region, and the impeller will be rotating with an angular speed of 1000 RPM. Let us select that region. It is selected. Green check. Next one, we have to apply boundary conditions. That means environmental condition at the exit locations. Let us select those locations. Boundary conditions. Insert boundary condition. It will be atmospheric pressure or environmental pressure at the exit location and the inlet locations also. Select, grain check. We have to provide 2 more boundary conditions, so we can cut it along some specific plane. Let us cut this one along right plane, green check. Now boundary conditions, inside boundary condition we have to provide atmospheric pressure at the entry location. Selected. Another location you can select here. Selected, green check. So all the boundary conditions have been applied properly. Now we can select the goals. Select. Initially we want to see some surface goals, but at the same time we want to find out shaft torque also. So insert surface goal. First of all we have to select the shaft torque. Shaft torque, you can see here the direction of torque. It will be actually, if you see that object, direction of torque will be actually along Z, right? So this is the shaft, direction of torque will be along Z. We have to select the shaft. Selected, green check. We have provided the goal to determine shaft torque. Again, some other goals are required. We can select some surface goals again. Surface goals at the exit location. We want to find out pressure, temperature, velocity, etc. at the exit locations, right? We want to find out average temperature of fluid, average pressure and velocity also at the exit location. So for the exit location, select other. You can select the lead number 1. Selected, green check. Now all the goals have been defined. Now you can run this. Let us start a new calculation. Solver window has already started iterations. Mesh preparation is going on. The solver is finished. We can see the results, like average temperature of fluid at the exit surface is 20.0033 degrees centigrade. That means we don't see that much of change in temperature at the exit location. And pressure also we can see a little bit of less. Initial pressure was 1 bar. You can see that torque is 0.028 Newton meter and average velocity at the exit surface is 0.33 meter per second, and average total pressure at the exit location is 0.995 bar, and the temperature is 20.0033 degrees centigrade. We don't see that much of change in temperature. Next one we'll see the different cut plots and dynamics of flow particles. Next to that we'll go for some kind of parametric study and analysis. Now we'll see from the results cut plots. And for seeing the dynamics of flow particles and cut plots, etc., let us make the model completely transparent on the geometry itself. Let us select that model and make it completely transparent. The model is transparent right now. Now we can see the dynamics of flow particles and different cut plots. First of all, we want to see cut plots from different planes. Cut plots, insert. We can see cut plots from both front plane and right plane. We want to see pressure, velocity, etc. Let us see velocity at the beginning. And contours and vectors we will see. We have to select the plane across specific location, right? We can drag it a little bit, then you can see. Green check. It is generated. We can see this one in the form of an animation. Couplet 1, display. You can see velocity is not that much of changing along the inlet location, but while passing through the impeller it is changing, and it is indicated by the change of color. I can see pressure also. Let us see pressure distribution. Similarly, at the inlet location, we don't see that much of change in pressure, and actual pressure variation occurs while passing through the impeller to the exit location. Let us clear and hide this part. We'll see surface plots, insert surface plots, and we want to see all faces. Green check. At the boundary, we can expect zero velocity. It is okay. Let us clear and hide this part. And next to that, we'll go for some kind of flow trajectories. That means we want to see dynamics of flow particles through this centrifugal pump. So flow trajectories, and before applying these flow trajectories, we have to cut this model along some specific planes. Let us cut that along front plane. Then flow trajectories, insert flow trajectories. Instead of 20 numbers, we want to see 100 numbers. And instead of pipes, we want to see in the form of arrows. We are selecting the exit location. I have to select the inlet location also. So we can select other, and the lead number 3 is selected. Green check. It's ready. Let us run this. Flow trajectories, clear and hide. Let us play. Better to see the complete view of this model. This is the complete model. I can see the dynamics of flow particles, how the particles are moving. Velocity of these water particles at the inlet location is very less. It is 0.62 meter per second, and as it is coming near the impeller, its velocity is increasing. It is in the range of 1.26 to 2.5 meter per second, and similarly at the exit location also, its velocity is very less. It is below 0.632 meter per second. Okay, let us clear and hide this part. Next one, I want to see our goals. From the goal plots, insert goal plots. We have already seen the results from the SolidWorks window. We want to see all these things in the form of graphs. Let us see all these results, then we will see from the graphs itself. Summary and history. You can see here the torque is in the negative region because we have considered angular velocity negative to provide a specific direction. And you can see after 120 numbers of iterations, total pressure is 0.99 bar, and temperature of fluid, we can see here it is 20.033 degrees centigrade. And finally, you can see velocity at the exit surface it is in the range of 0.32 meter per second. So these are the results. Excluding these things, we can have surface plots. That means at different regions we can have pressure, temperature, etc. across the path. So let us see that's XY plots. So we have to see XY plots, insert. We can see XY plot along entry to the exit locations, but from entry to that impeller position we don't see that much of changes. Better to see this XY plot from impeller to the exit locations. So we are selecting all the parameters like density, pressure, temperature, etc. And to have a better accuracy, we'll change the resolution to higher value. Now we have to select the specific line along which we want to find out XY plots. That can be obtained from the geometry itself. Let us select the line. The line is selected. Now we can see the XY plots along this path. It is already generated. You can see the XY plots along this path from the impeller to the exit locations. We can see density value has increased at the exit location. Similarly, pressure also increased from 0.99 bar to more than 1.03 bar at the exit locations. Even you can see temperature also. Temperature is reduced a little bit. For the solid and the fluid, you can see the same trend of temperature distribution. And velocity also, you can see from the impeller to the exit location, velocity is increasing. Final velocity at the exit location is 4 meter per second, and initial value was less than 1 meter per second. So you can have a lot of other things like velocity x, y, z directions, and also we can have different things like vorticity, relative pressure, then bottleneck number, and also we can see shortcut numbers. Detailed analysis of all these graphs can be done using Excel with more data with a higher accuracy. Next to that, we want to have some parametric study, and in that parametric study, input variable will be angular velocity of the impeller, and based on that we have to find out pressure, temperature, velocity, etc. at the exit location. So next one, we have to go for some kind of parametric study. We'll start from solve and new parametric study. In this new parametric study, we will consider the angular velocity of the impeller as the input variable, and that will come from output parameters, and that will come from the simulation parameters, and we are adding these simulator parameters. It will come from rotating regions, and we are selecting angular velocity as the input variable. Go and check. We have to define that angular velocity. We are considering design of experiments and optimization, and the angular velocity should be defined with a defined range. Let us consider angular velocity from 20,000 rpm to 500 rpm. Go and check. Now to select that goals, it will come from output parameters. Let us select the goals. We can select all the goals, that means pressure, temperature, etc., velocity, etc. the exit location, by the same time torque of the shaft also. Go and check. Let us select that scenarios. 5 set of experiments to be determined. Let us create. So with these different angular velocities, we have to find out our goals, right? Let us run this. The solver has already started. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. Okay. You can see how the iterations of 4 set of different results are going on with different angular velocities. The solver is finished. We got the results from the parametric analysis, and you can see that all this pressure, temperature, velocity, even torque, etc. all are varying with angular velocity. And with the minimum angular velocity of 500 revolutions per minute, we got the torque equal to 0.2067 Newton meter, and total pressure is 0.994 bar, and temperature of fluid is 20.001 degrees centigrade, and finally velocity of water at the exit location is 0.168 meter per second. And with the maximum angular velocity of 20,000 revolutions per minute, we got the torque of the shaft equal to 10.8 Newton meter, and total pressure of water at the exit location is 1.57 bar, and temperature of fluid also 21.92 degrees centigrade, and finally the average velocity is 7.11 meter per second. So we can see that there is a linear relationship between pressure, temperature, velocity and torque with the angular velocity. More the angular velocity will get, more the velocity, pressure, temperature, etc. at the exit location. From this data, suppose we want to go for some kind of optimization of our output results. Suppose we want to have a velocity of water at the exit location to be 5 meter per second. For that, we have to select angular velocity in the range of approximately 15,000, right? In the next analysis, we have to optimize the angular velocity in which we can have average velocity of water at the exit surface to be 5 meter per second. Okay. So we'll start another analysis. Solve new parametric study, and you want to go for optimization, goal optimization. In this case, we have to depend on input variables, and again in this case we are considering input variable to be angular velocity of the impeller. Let us select that one, and we have to specify a range of that one. We are selecting the range from 15,000 to 9,000 rpm. Green check. And let us see the output parameters. From the output parameters, we have to select the goals. In this case, we have to optimize one goal, that means average velocity at the exit location we want to have to be 5 meter per second. Let us say the target value, and target value should be 5 meter per second. We want to have a variation in the range of plus minus 0.1 meter per second. Now let us see the scenarios. Let us run this. It will start iterations with the maximum RPM. Next one, it will start with the minimum RPM. In this way, it will try to minimize the gap, and finally it will optimize. The solver window has already started iterations. Let the iterations move on. Whenever it is finished, we'll see the results. Okay. The solver window has finished. Our solution is converged. We can see after 6 set of experiments on design point 6, we got the solution converged, and we can see that when the angular velocity of the impeller is 14,377.43, we got the average velocity at the exit surface to be 4.9 meter per second. So this is our results. In this case, the discrepancy is 0.099 meter per second, is very less. So from this optimization, we got optimized the impeller velocity to have a specific output. That means to have a average velocity at the exit surface to be 5 meter per second, we have to provide the impeller velocity to be 14,377.43 revolutions per minute. Okay. So this is all about our today's analysis. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.